Welcome back. Uh, in the last segment, we introduced this uh, tensor, the symplectic form, which has slots for two vectors and is anti-symmetric. And I mentioned that it plays a role that is somewhat analogous to that of a metric tensor. It produces mappings between vectors and covectors. All right. Uh, Big difference, of course, is that the metric tensor is symmetric. This is an anti-symmetric object. So what we would like to be able to do now is say, okay, you can do lots of interesting things with a metric tensor. What can you do with a symplectic form? What can you do with this additional symplectic structure? Uh, Very good. Uh, what we're going for is something beautiful. If you have a metric tensor, then a metric tensor allows you to do transformations of vectors in such a way that the scalar product of those two vectors remains the same, right? The corresponding transformations are called orthogonal transformations and play an important role. It leads you to the group of orthogonal transformations, the orthogonal group, the group of rotations. Uh, can you do something similar with a symplectic form? Once you have two vectors and you apply to them the symplectic form, you get a number. What are the transformations that keep those actions of the symplectic form, those scalars, invariant? That also gives rise to groups of transformations that are a symmetry. And as we will see, and this is what is the whole reason why we're doing this, is that those transformations form a group. It's called the symplectic group. And the transformations are called symplectic transformations, naturally. But in physics, they're called canonical transformations. So what we're going to see by using this additional structure provided by the symplectic form is we're going to see the whole uh, formalism of Hamiltonian dynamics that we're familiar from classical mechanics appear. So let's do that. So here we go. We have a space. It's a large space. It's completely crooked and curved and all that. The space that we consider here is the cotangent bundle in which we have embedded the simplex, added an extra dimension so that we don't have to worry about normalization, and then added all of the cotangent spaces to produce a bundle. So this guy is 2n dimensional. The coordinates are going to be n thetas and n pi's, and we write this in simplified or in a simpler form by writing it with this complex index alpha I. Very good. Uh, if we have a vector field, we can integrate this vector field for at each point you have a vector, and you can figure out what are the curves that are tangent to the vector field everywhere. So what we have here is a congruence of curves, of integral curves of the vector field. So what we have done there is we've taken a vector field that has components, and these are the basis vectors, it has components. We integrate these components, so we write the components, the lambda, these guys are the components, the alpha I, and of course this is a function over the whole space. If I give you these components everywhere, I can go ahead and integrate to find these guys as a function of lambda. And these are the curves. Okay, this such curves, I give you a vector field and I integrate to find the integral curves. This is called, or one of the words people use is this is called a congruence, of course, but this is called a flow because it really resembles the flow of a fluid, right? At each point, there is a vector. The vector is tangent to the flow lines. What we would like to have is we would like to consider those flows that are natural in this for this particular manifold. In particular, the flow that we're really concerned with is what is the flow along which or relative to which the symplectic form is conserved. This is this is going to be truly asymmetry. Well, what is typically asymmetry? Well, asymmetry is when you do a transformation of some kind and something does not change. In the particular case we're concerned here is what if you were to move along this flow and the symplectic form does not change? This is expressed by saying the Lie derivative of the symplectic form along that particular vector field is equal to 0. So we would like to figure out what are the particular vector fields that satisfy this equation. So let me go back to a lecture a long time ago, namely last lecture, where we wrote down what the Lie derivative of any tensor with two slots, like the metric tensor, looks like. So we recall now that we have an expression for such derivatives, and I'm going to just write it down because now we have more indices. We have those alpha j i's and beta j's. So this is what this guy looks like. The Lie derivative of omega has components alpha I, beta j, and this is going to involve the components of the vector, which we're going to write as gamma k, then the gradient gamma k of omega alpha I beta j. That's the first term. What we're doing is we're taking the components of the symplectic form and we're taking the gradient, the derivative, in the direction of the vector field. Next, we add the, this is going to be gamma k, beta j, gradient alpha I, b, b gamma k, plus, so this is, all these guys come with plus signs, alpha I, gamma k, gradient beta j, v gamma k. And that's it. Now this looks awful, and it is. The first piece is just the derivative. If you're going to take a derivative of omega, at some point you have to have derivatives of the components, right? So that's the first piece. The second piece, however, is you use the omega here and you contract with the vector, and the two indices alpha I beta j appear here, beta alpha I beta j, and then the other you have them in the opposite order. It's here it's the first index that acts on the derivative of v. Here it's the second index that acts on the derivative of v. Very good. This is what we have to solve. Remarkably, it's not that difficult. Um, Recall also that the symplectic form has very simple components. It was basically zeros and ones and minus ones, and it takes this form. So this is just zeros and ones and minus ones. So this immediately tells you that whatever derivative you're going to be taking of these zeros, ones, and minus ones, this guy is going to vanish, and therefore the Lie derivative of omega I beta j is the sum of two terms. And so what I'm going to do next is I'm going to say, well, it's those two terms. Good. But because these guys are constant, I can bring the omega inside the derivative, and I can bring this omega inside the derivative, and the result is alpha I omega gamma k beta j v gamma k plus, or I'm going to put this as a minus here, minus, gonna have that derivative um, beta j, I'm gonna bring it inside, and I'm doing, did I do this right? Let me see, alpha I gamma k, alpha I gamma k, yes, this is correct, alpha I gamma k, oh, I have a minus sign, an error here. Here this contracts with the first, there it contracts with the second. Ah, yes, my error here. This is going to be gamma k, mm, um, gamma k beta j v alpha I. Yeah, sorry about that. It's just getting these too many indices. Very good. Now, what does this look like now? Do you see? Oh, do you see that I flipped the sign? The reason I flipped the sign is that this was alpha I gamma k, and this is in the opposite order, gamma k alpha I. So that this is, since this is antisymmetric, I flipped the sign. Now this looks awfully complicated, but let's look at what we have aside. Uh, what we have here is some derivative with an I, and when I look here, I'm summing over the gamma case. So what I have here is an object with an index downstairs. Let me write it like this, Vj. Then a minus. And then I have the derivative j. And here I also have the gamma case, but I have an I downstairs. So this is the object here is Vi. And what we are doing is we're setting this whole thing equal to 0, right? That's the basic idea here. We want to figure out what are the V's such that the derivative of the symplectic form, the Lie derivative, vanishes. What are the particular flows such as that you move along the flow, the symplectic form is preserved. So this is going to vanish. So this equation looks something like this. And if you look at that, this is a curl. And everybody knows what the solutions to equations like this look like. If the curl of a vector vanishes, then the vector itself, the vector itself must be the gradient of a scalar, of a potential. Uh, Very good. This is in many dimensions and it looks pretty awful and nasty, but the equation is exactly the same thing. So what we're going to claim is we're going to use Poincaré's lemma, which says that this is actually pretty much true in all cases of interest. Uh, we're familiar with these things from electrodynamics, but it can be made more general. And what we would like to do here is we're going to play a little bit of a dirty trick. So what is our solution to equations like this? It's going to be that whatever these vectors here that appear inside here are, whatever these objects, monstrosities that appear here are, they're going to be gradients of scalars. Since this object, this vector here that appears with an index downstairs is the gradient of a scalar, let us call the scalar by the name V, so that the two are associated. This is the covector associated to that scalar. So our solution, the vector fields that lead to flows, integral curves, such that the Lie derivative of the symplectic form vanishes are such that this particular object here, gamma k alpha I gamma k, is going to be the gradient, the component alpha I of the gradient of a scalar function. Or if we want to write it in a somewhat less messy notation, if you take the symplectic form and you apply it to the vector field V, these are supposed to be parentheses, and what you get is going to be a covector. That covector is the gradient of a scalar function, and this object is also going to act on vectors. We are now ready to do some magic. The magic is the following. Well, of course, we can check. Okay, we can check that this actually works. We can substitute back. We can substitute back to make sure it works. If you have the in this equation, we're going to substitute our solution into this. We have a solution for what this vector looks like. We're going to substitute back here and check that it vanishes. So we can do that. This guy, alpha I beta j, this is going to be alpha I, and here we're going to apply our vector. This guy here is going to be this object, but now with beta j of a scalar. And then we're going to have a minus the beta j of the same object, but now it's alpha I v. And so you see what we have here. You just have gradients taken in the opposite order. Those commute, you get 0, it works. So we have the solution. So what do we do with it now? What we would like to do now is go back to this equation here and make sure we understand. We want to explore the consequences. We want to go back to this object here where V now is very special. V, the covector associated to V is a gradient, right? So this guy is very special. This is the gradient of a function in this large dimensional space. Very good. Let me write it in a different way. Remember how this guy worked? This was the theta I acting on V. This guy was supposed to be a theta pi this guy reflects the first slot. This guy, the gradient of pi, reflects the second slot. And then minus the gradient of pi, tensor the gradient of theta. So this is all the same here. And if now here we put the v, and here we put the v, what we have on the left hand side is v v1, okay, v1 alpha, which is v1 alpha, and then we have gradient of pi minus v2 alpha gradient of theta. All right. Next, this guy, we know what that is. This is the theta 1, the lambda, and here we have the gradient of pi I. And here we have, yes. And then minus, here we have the pi, sorry, 1I, 2I, that's better. And here we have pi I, the lambda, gradient theta I. All right, this is the left hand side. So let me write that here, left hand side of this equation. We expanded it in full glorious detail. The right hand side is just the gradient of this function of thetas and pi's. So this right hand side, we can just say, take that function, differentiate with respect to theta, and then take the gradient of theta, plus take the derivative of that scalar function with respect to pi, and then take the gradient of pi. All right. So what we have here is a covector on the left-hand side, a covector on the right-hand side. This left-hand side is expanded in terms of the basis. They're here, the basis covectors. So is the right-hand side. Let's equate the coefficient of gradient of pi. And what we have is that d theta I, this is an I later, d lambda is equal to dv v pi. And when we look at the second term, d pi I d lambda, there is a minus sign there. Is equal to minus dv d theta. These are the equations of the curves in terms of a scalar. You give me a scalar and these equations will reproduce a flow such that the symplectic form is preserved along the flow. You can't help but noticing that these are exactly the equations that you expect in Hamilton's equations. If the parameter along the curve is called time and the scalar function that you have here, we call that, uh, if that scalar function, we call that Hamiltonian, then what we have here is that the rate of change of the coordinate is equal to the derivative of the Hamiltonian with respect to the momentum, and the rate of change of the momentum is equal to minus the derivative of the Hamiltonian with respect to position. What should we derive or conclude from this? What this tells you is that the structure of the equations of classical mechanics is essentially of a very geometrical nature. Once you have coordinates and associated momenta, the coordinates on the cotangent spaces, we're going to interpret the coordinates on the cotangent spaces as the momenta conjugate to the position coordinates. But here we're talking something that has nothing to do with classical mechanics. The formalism is exactly the same, right? So this is a remarkable result. The equations of classical mechanics are what they are basically because you are preserving a symplectic structure in some phase space, some cotangent bundle. It's completely generic. We're going to use this to do quantum mechanics, okay? Uh, so that means that quantum mechanics is of exactly the same form as classical mechanics. Only it is of the same form provided you recognize that what you're talking about is the dynamics of probabilities, not the dynamics of positions. You have to let this sink in because it's an amazing result. Of course, nothing in what we have said here tells you anything about how do you know that lambda is time? Is any curve uh, parameterized by a lambda the same as being parameterized by time? Obviously not. If you don't know what this is time, how do you know what is the object here, the scalar that generates the evolution in time? So clearly we know nothing about how to choose, how we do not know nothing about how to choose the pi's so that they correspond to whatever the momenta are, such that when you preserve the symplectic structure, the parameter is time and the uh, scalar function, the Hamiltonian function, is actually the Hamiltonian. Nevertheless, it's amazing to see where the structure is coming from. The functions v, the scalar functions, are called the Hamiltonians. The here we have the components of a vector, right? These are called the Hamiltonian vector. The vector v, the vector v with components like so, is called the Hamiltonian vector associated to the Hamiltonian uh, v tilde, the scalar function. Now in physics we normally do not do that. We call the Hamiltonian the particular scalar function that leads to evolution in time. More mathematically inclined physicists or mathematicians just call any v that has these properties a Hamiltonian function. Very good. We can do a couple of more things that are very interesting. Suppose that I were to compute the action of the symplectic form on two Hamiltonian vectors. So what I mean here is I just apply it on two vectors as we saw that, so that where uh, v is dd lambda and u is dd mu. Suppose I were to do that, then what we would have here is the components of v, then the components of u, minus the other way around, the theta d mu. Very nice. But if these guys are Hamiltonian vectors, if v and u are Hamiltonian vectors, in other words, they induce a flow that preserves the symplectic form, then we know that these guys here are given by expressions of this form, by gradients, right? By Hamilton's equations. So let us substitute v, u. We substitute here, and what we have for d theta d lambda is dv, d pi. And what we have for d theta d mu back there, so there is another a slot, a minus sign d theta d mu. There we have, I'm sorry, here there was a minus, yes. And what we have for this guy is going to be a minus, well, let me just do this order. This guy here is going to be d pi d mu, that's going to be d, we need a, what, yes, u, and this is going to be d theta I. And then for the other one here we have d v theta I with flip the sign, d phi I, and this is the u, the theta I. Very good. Let me see. This guy gets you something here, and this guy we d pi d mu, we get this, and it flips the sign. So there is a sign change here. This is minus, and that is plus. That's good. One of them keeps the same sign. The other one, the one that is a d pi, flips the sign. So you get a minus sign in the front and the side. Very good. What we have here, you may recognize as the uh, Poisson brackets of v uh, dv Did I do this right? I have something wrong. Yes, of course I have something wrong here. D theta, d pi d mu, d pi d lambda. This, yes, this is here. Ah, I knew there was something fishy here. The pi d lambda is the I d theta with a minus sign, and this is the d pi. Sorry about that. Very good. Um, so this is by definition what we call the Poisson bracket of the two fields. So here we have another interesting conclusion. Let me write it in the next page. The action of the of the symplectic form on two Hamiltonian vectors is the Poisson bracket of the corresponding Hamiltonian functions, where this here is the Poisson bracket. So this is where Poisson brackets come from. The Poisson bracket is a clever way of writing the action of the symplectic form onto Hamiltonian flows. Very good. One last thing, and it is the following. Suppose that you have a genetic functional of x of the point. So this is just some generic function on the cotangent bundle. This is a function of the thetas and of the pi's. When we figure out what the change of this function is along some curve along the field, along a Hamiltonian field, this is going to be, just take the derivatives and then take the components of the vectors. These are just directional derivatives. And here we write this as df d theta, d theta, d lambda, plus df d pi, d pi, d lambda. But here we can use Hamilton's equations. This is going to be the derivative of the Hamiltonian field with respect to the momentum. And here we have the f, the pi I, and here we're going to have minus the derivative of the Hamiltonian field with respect to the coordinate. So again, we have the same structure as the Poisson brackets. So the conclusion is that the rate of change of a function along a Hamiltonian form, along a Hamiltonian flow, is going to be given by the Poisson bracket of the function itself with the scale, the Hamiltonian function that generates the flow. I think that this is basically what I wanted to say. Let me conclude by summarizing the formulas again for the case when the parameter tau is lambda, time is the parameter lambda, and h is the Hamiltonian flow. So in that case, we have Hamilton's equations, d theta, d tau is the derivative of h, a scalar, with respect to pi. D pi, d tau is minus the derivative of a Hamiltonian function with respect to the coordinates. Furthermore, the derivative of any function with respect to time is going to be given by, well, if you have a vector, it's going to be the vector acting on the function. But this is exactly the same as the Poisson bracket of h, f and h. And the vector, in physics we never talk about the Hamiltonian vector, but clearly there is a vector. The vector h is dd tau. And that vector is just going to have components. The components are going to be pi I with basis vectors minus components with basis vectors d pi. This is a wonderful achievement. The fact that we have isolated an incredible amount of the mathematical structure of classical physics, but now for the dynamics of probabilities. What we're going to see as we proceed is that this is, because it is a dynamics of probabilities, this is exactly the same mathematics we're going to use for quantum mechanics. But there is one thing here that we have not done properly yet, which is, how do you know which H's to choose? Or even better, how do you know which V's to choose? In the next lectures, I'm going to make the claim that if you impose not only that the symplectic form be conserved by the evolution, but you also impose that a metric tensor is conserved, then you're halfway towards quantum mechanics. Okay, so quantum mechanics will involve not only a flow that preserves symplectic structure, but also a flow that preserves a metric structure. That is for next class. See you then.